Okay, so this is part 4 of the video tutorials to go with CNF's cone fundamentals and cone isolating stimuli tutorial Matlab code. And you should have already watched parts 1 to 3, which would bring us down here to line 606 in the current version of the code. Now what we've shown above is that cone fundamentals are a linear transformation of color matching functions, and we've discussed confusion lines and showed that the intersection point of multiple confusion lines for dichromat overlay the cone isolating chromaticity when we plot them in a chromaticity diagram. And now what we want to do is show that we can use the confusion lines for the 3 types of dichromats, protonopes, deuteronopes, and tritonopes, to actually identify the linear transformation that takes us from color matching functions to cone fundamentals. The resulting cone fundamentals won't be normalized in any particular way. That is to say, their peaks may have different heights, but their shapes will be correct on the assumption that each class of dichromat is missing one of the 3 classes of cones. So how do we do that? We've already shown how to get the confusion lines, and we have those calculated above. So what we do, I'm going to rerun this tutorial down to here just to make sure I have all of the variables that I need in my Matlab workspace, but we've done that before. We're going to fit each of the confusion lines with a line. This is imagining that rather than having generated these confusion lines ourselves, we had measured them in experiments by having dichromats do color matches multiple times to various test lights and looking at the spread of those. So we imagine we've got measured points on confusion lines. We want to fit them. We just do that by simple linear regression, fitting the R and the G coordinates of the confusion lines, treating those as x, y in a plane, and finding the equation basically, in this case, G is equal to A times R plus B, the standard equation for a line, and that's done by the / command in Matlab after you put the R values in one column of matrix and ones so that you'll handle the constant in the other, and make the target the G values or the second coordinate, the confusion lines, and we'll do this for all the confusion lines we have, and that will give us these fits. Okay. Now, given that fit, what we want to do is find the intersection point of all the confusion lines we've just fit, and for each one we've got it in the form G equals A times R plus B. We can rewrite those in the form minus B is equal to A plus R minus G for each fit line, and that gives us basically a set of linear equations, all of which should be solved by the same R and G, which we can then set up in matrix form and again solve using regression in Matlab. So what we do is we set up a matrix where the first column is the A values that we got from the confusion line fits. The second column is -1 to handle the minus G, so that's here that would multiply the RG that we want to solve for, and we create a negative B from the second coordinates of the confusion line fits, and then we just do the little linear regression, and that gives us in a column vector R and G at the copunctal point. So we'll do that for each of the 3 classes of dichromats, getting us 3 so-called copunctal points, points where the confusion line for that that class of dichromat intersect. So I'll run that, and if we just look at copunctal point 3, it better be a column vector. There it is. That's the intersection point. Now we've already made a plot in chromaticity diagram with one subpanel for each type of dichromat, and the spectrum locus and the confusion lines, and you can see where they intersect. So now we're just going to go take that figure, bring it back up, plop onto it in yellow the copunctal points that we just solved for, and show that they lie where they ought to lie. So here they are, and we see this nice little yellow point at that point of intersection sitting right on top of the plotted cone isolating chromaticity for the protonope, the L cone, for the deuteronope, the M cone, and the tritonope, the S cone. And so now we have derived, not by knowing them in advance, but by finding the intersection point of confusion lines, where those cone isolating stimulus chromaticities are in the RG plane. And again, if we were doing this with measurements, what we do is, for example, take a protonope and do a color matching experiment where we found the RGB color matching values multiple times, so there'd be some scatter because the protonope will make confusions. Do that for multiple test lights, plot them in the chromaticity plane or compute the chromaticity, and then do this fitting procedure I've just described. That would give us now these 3 points. Super. So we've got those. Now what we're going to do is use those recovered points to get the transformation that gives us the cones from the color matching function. So up above, we noted that we could calculate, in fact we used this line of cone, the cone isolating direction RGBs were given by the matrix M cones to color matching functions applied to 1, 0, 0 transpose, 0, 1, 0 transpose, and 0, 0, 1 transpose. And we note that this is just the identity matrix, so that this matrix M cones to color matching function is interpreted as having in its columns the cone isolating RGB directions. Now we've just found the chromaticities of those directions, and so what we need to do is convert those chromaticities or promote them to RGB with some arbitrary length, because we don't know the length, and then just put them in the columns of the M cones to CMFs matrix, invert it to get a matrix that takes us from M CMFs to cones. Because we'll have to make up the length of each of those from the chromaticities of each of the RGB vectors for the cone isolating directions, we won't get the cone fundamentals normalized in any particular way, but that doesn't matter to us for most calculation. It affects the scale of the fundamentals, but not the shape. And if you want later to verify that using just some choices of scale when I make it up below doesn't matter, you can just redo this using other choices of scale and see what happens. But so here we'll take the copunctal points that we've solved for, and each one is RG chromaticity in the first 2 rows of a column vector. We'll tag on 1 at the end as an arbitrary chosen intensity, and that will give us a copunctal RG, and I'm calling that third value Y. And then we convert back, just doing a little algebra that takes us from the first 2 chromaticity coordinates and an intensity back to full RGB values. And that calculation is implemented in the Psych toolbox in the function xyy to xyz. It just inverts the function xyz to xyy. You can go read it if you want to see the math required to go from chromaticity and, in this case, luminance over the made up arbitrary length back to something which has that chromaticity but is now promoted to the full tristimulus coordinates. So we'll run that. Then we're going to invert that matrix to give us an M color matching functions to cones underscore copunctal derive to say where it came from. And that matrix then will have, and we can apply that to the styles 10-degree color matching function at 1 nanometer multiplied by this matrix to get derived cone fundamentals based on the dichromatic confusion lines that we've derived here to get us derived cone fundamentals. So we'll do that. Now these have arbitrary scale, so we're going to have to normalize it. And actually, it turns out there's no particular guarantee even that the cone fundamentals we got back were positive. So we're going to find the point, the index of the point in the derived cone fundamentals with the maximum absolute value. And then we're going to divide each of the derived fundamentals by the corresponding maximum point with maximum absolute value, but we'll derive by the sign value, and that will give us normalized color matching functions whose maximum is each 1. And so now we can do a figure where we'll plot the actual Stockman-Sharp cone fundamentals that we used up above when we introduced the whole ideas, and then we'll plot our derived cone fundamentals that were derived from the color matching functions from the copunctal points, normalized the same. And so here they are. The red, green, and blue are the actual tabulated Stockman-Sharp fundamentals, and the dotted lines are the ones we've just derived by applying a linear transformation, which we figured out from the confusion lines, to the color matching functions. And you can see that they agree perfectly in this case because there was no noise in anything. So this method of deriving cone fundamentals from the color matches of dichromats, these are the so-called Konig type fundamentals. And Konig actually used this technique, as I understand it, to derive one of the first quantitative, perhaps the first quantitative estimates of cone fundamentals that are in reasonable agreement with modern estimates. So with that, we've really taken you through one slice of rather fundamental color science from the beginning to the end, talking about color matching functions first in a lecture and their linearity properties and matrix vector multiplication. And then from that, the fact that cone fundamentals must be a linear transformation of color matching functions. And then in 4 parts of a tutorial that go with this Matlab script, we've illustrated those ideas in code and plots showing how they work out. And if you go through and master this material, you will be in good shape as a computational colorimetrist.